Okay, for Algebra 9.1, we're starting a new unit. This is all about quadratics. And if you remember what the word quadratic means, it seems like it should have an exponent that's to the fourth power because the prefix quad means four. But actually, I hope you remember from previous units that it means that the exponent is actually squared. So anytime you have a squared a term, that means that it's going to be a quadratic function. So this is what a quadratic function looks like on a graph. Remember, in the past, we've done like linear, which would be a straight line, and we've done like exponential, which is where there's a little bit of a curve and it shoots up really fast. But in a quadratic, it makes this fun U shape, and this U-shaped graph is actually called a parabola. So when you look at this, it looks almost like it's pronounced parabola, but you actually pronounce it like parabola. So in a parabola, that's just the shape of this graph in a quadratic function. Anytime you have anything squared, y equals something squared, like you do in these, it's going to form some type of a U shape. Sometimes it's right side up like this, where it's opening up, and sometimes it is opening down, like down here in problem 1. So, and sometimes, I don't know if you can tell, but this one's wider, and sometimes it is narrower. So a lot of what's going to depend on whether it's wider or narrower is going to be the numbers that are in front of just your x squareds, or the numbers that are added after the x squareds. So in order to, well, we'll actually talk about that part later. Let me first mention this axis of symmetry. So what you might notice about this parabola is you could exactly fold it in half. Like you can take one half and perfectly, if I get my finger right there, perfectly flip it over and it land exactly symmetrically on the other side. So, and it's not always right in the center. Sometimes a parabola might be over here. But what will always happen is there will always be a center where it could be folded over, and that is called the axis of symmetry. So in this particular case, my axis of symmetry is on the 0, but in this case, my axis of symmetry might have been like on 2 or whatever. So you're always going to have a center point that then it starts to open up and go back the other direction. Okay, you're also always going to have this thing called a vertex. A vertex is the lowest point before it makes the curve and starts to turn the other direction. So in this case, the origin is the vertex, and in this case where I just made this up, the vertex is a little bit lower. It might be like down at -2 or something like that. So, well, to -2, really, because a vertex is going to have, it's going to have a coordinate, like an ordered pair. So, and this one would be 0, 0. So this is the vertex, and the dashed line through where it could be folded over is called the axis of symmetry. So a parabola is the U shape, the axis of symmetry is where it can be folded, and the vertex is the lowest point, or it could be the highest point of a graph, depending on if it opens up or if it opens down. So that is the vertex. So speaking of if it opens up or down, if it opens up like this, it would have a vertex that's at the lowest point, which makes it a minimum. Okay, if it is an upside down parabola, if it opens going down, then it would have a vertex up at the top, which would be its maximum point. So if it opens up, it's going to have a lowest, it's going to have a minimum vertex. If it opens down, it's going to have a maximum, and that just makes sense because once it gets to its highest point, it's going to turn and start going the other direction. Okay, so for problem 1, we are going to identify the vertex. So what is the coordinate of each vertex, and is it a minimum or is it a maximum? So the vertex in this one starts to turn and go back down right here. So we need to write down that the vertex is 0, 3. Oh, actually, they already did that. The vertex is 0, 3. And because it reaches its highest point, that is called its maximum. Okay, and this one's already done for us too, but let's double check to make sure you guys know how to do it. The vertex here starts to turn and open back up at its lowest point here, which would be 1, -1, which they wrote down for us. And because it's the lowest point, it is a minimum. Okay, so now let's do the you try. This would be a good time to push pause in the video and make sure you can do it. Okay, just checking. I want to make sure that you guys got that the vertex is -2, -3. That's the vertex, and it is a minimum because it reaches its lowest point. Minimum. There we go. All right. Let's go on to problem 2. Now we're going to actually graph it. They actually graph this for us. So they want to take the regular x squared. I don't think I talked about the parent function yet. No, I guess we'll talk about that later. So the parent function is just y equals x squared. That's kind of what we usually compare everything to. So we're going to take y equals now 1/3 of it, x squared. So this is what we compare everything to. It's actually called the parent function because it's like the most basic quadratic equation you could ever graph. And we're going to compare it to what we are now going to work out, which is 1/3 of that. So to start, you make a table of values, which they've already done for us. They plugged in 0, 3, and 6. So they took 0 squared times 1/3, then they took 3 squared times 1/3, then they took 6 squared times 1/3, and these are the answers they got. And they put those points on there, and then they reflected it over because a parabola reflects over the line, the axis of symmetry. So you really only need to pick 3 points. Once it starts to turn the other direction, whatever point you had over here, you can reflect over and put it on the other side because they're going to be perfectly symmetrical. So real quick reminder what the domain is and what the range is. Domain deals with our x's. So that's how far this parabola goes left to right. And it may look like it stops right here and right here, but because there's arrows, what that tells you is it's going to go on and on and on and on forever at a slight angle out. And the same thing over here, forever and ever at a slight angle out. So how far left and right will this graph be? If we took a straight line and we were like, will it ever touch here? Yes. Will it ever touch here? Yes. Will it ever touch way down here? Yes. I'd have to go really far up, but it would touch. So what happens is it's saying that it would touch everywhere from left to right. So that is why the domain on the x-axis would be all real numbers because this parabola keeps going out in everywhere. So from left to right, you could put a ruler or a line everywhere left to right, and eventually it would touch. But the range is talking about the y direction, which is going this way. It touches everywhere, way up here and here and here, and it touches twice, touches twice, touches twice, touches twice. But once you get past 0, it doesn't touch our parabola at all. There's nothing below 0. So that's why the range is only all the numbers greater than or equal to 0 itself. It only touches the parabola going up the graph. It's never touching below. Okay, so now it's telling us to try. So how we would do this is we would start by making a table of values. And I would always pick, if I were you, a 0. That's going to be easy. And remember, you have to plug it in. This is for x. You have to plug it in with the order of operations. So if we're making x 0, this is 0. What is 0 squared? You can't say 0 times -3 first. You have to do exponents first. So 0 times 0 is 0. 0 times -3 is also 0. So this parabola is going to have a dot at 0, 0. Okay, let's pick a negative maybe 1. So -1. So -1. When we plug in -1 for x, remember you have to do the order of operations. So what is -1 squared? -1 times -1 is +1. +1 times -3 is -3. So we need a dot at -1, -3. So come over here and put a dot at -1, -3. All right, and then let's pick a +1. Let's just see. Let's pick +1. That should be easy to calculate. So when we plug in 1, I'm going to make it positive now. 1 squared, 1 times 1 is 1, times -3 is -3. So we're going to have a dot at 1, -3. So you're going to come over here and put a dot at 1, -3. So actually, I can see the start of our parabola. It's going to go this direction. I would normally go ahead and have you pick one more just to see, but obviously it's going to be off of our graph probably. Let's double check. 2, let's see where it is at 2. So if I plug in 2 for x, so I'm going to go up here and I'm going to make my x 2. So 2 squared is 2 times 2, which is 4. 4 times -3 is -12. Yeah, that's going to be way off our graph. So 2 -12 is going to be a dot. So over 2, -12 is going to be way down here, and that dot is going to reflect over, and it's going to be the same on the other side. So our domain, which is how far left and right it goes, is forever. Because eventually, if I put a dot going left to right, a vertical line like my pen is, going left to right, it would touch my parabola everywhere. So this is going to keep going out, and it's going to eventually just keep getting wider and wider and wider. So it would touch left to right anywhere. So the domain is all real numbers. Every number it will touch left to right. But the range is going the other direction horizontally. I'd touch with the parabola here, 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 here. But once I get above the 0, this is not touching my parabola at all. None of these include the parabola. So it's going to include all numbers less than 0, but nothing greater. So it's going to be y, the range is going to be y is everything less than or equal, because it's on the 0 itself, 0. Okay, let's go on to the next page and learn the rest of this lesson. What I want you to know about the widths of parabolas is the parent function, which I have mentioned earlier, y equals x squared, is like the most perfect parabola. It's just not very stretched out. It's not very, this is a pretty good example. It's like your standard parabola. It hits at 0, 0. It's not very skinny. It's not very wide. It's just kind of average. Now, anytime you multiply the number in front of x, it is going to stretch. So if I put a 2x squared, if I did something like y equals 2x squared, it's going to be just like this, but it is going to be stretched a little skinnier, twice as skinny and tall. So 2x is going to really stretch it this direction. If I do fractions, like y equals only half x squared, it's gonna squish it. It's gonna squish it more flat. So it's gonna go kind of like this. Okay, so the smaller the fraction, the more squashed it's going to be. But the whole numbers are gonna stretch it up. Okay, the other thing I want you to know, which we haven't talked much about, is negatives. If I had a negative, it is going to open down. So any negative, so let's say it's negative parent function, negative x squared. That's going to be pretty much the perfect parabola, like my center one here, except it's going to be reflected over and it's going to be opening down. So anytime you see a negative a term, it's going to be opening down. Okay, so let's say I had negative 2x squared. It's going to open down and it's going to be stretched a little skinnier. It's going to be a little tighter. And then the same thing with if I had a negative half x squared, it's going to be a little more squashed, a little more flat. But it is still opening down because it's negative. Okay, so let's look at these, and it wants us to put them in order from widest to narrowest. So right away, the 1/4 is going to be the widest. The parent function, this is the parent function, just x squared, is going to be pretty standard. This is going to be everything we usually compare everything to, because there's no extra numbers. And then the negative means it opens down, but the 4 means it's going to be stretched really long and skinny because we're 4 timesing this parent function. So the widest is this one, so that's why they put that one first. And then the parent function is kind of in between, so that's why that came second. and then the long, skinny, stretched one 4 times upside down is the narrowest. So now I want you to try. So push pause and do this you try, ordering from least to greatest, negative x squared, 3x squared, and negative 1/3 x squared. Okay, I hope you put that the widest one is the fraction. So this one, I didn't list it, but it's going to be first. The second most wide is going to be the parent function. This is an upside down parent function, but that's going to come in second. And then our narrowest will be the 3x squared. So you should have written that down third. Okay, moving on. Now we're going to talk about what happens if you, not just if you stretch it by, let me go back up here, by changing the number in front of x squared like I did here, but what if now I added a number at the end or subtracted a number at the end? So that is what they're doing here. They're adding or subtracting another term after whatever is squared here. So let's look at what happened. They took 2x squared and they graphed it. Here it is. It's stretched kind of skinny because it's just 2x squared. And then they did 2x squared plus 3. 2x squared looks the same as 2x squared, but look what happened to it. It shifted up 3. So it's still the same parabola. It's still the same skinniness. It's still narrow. However, instead of starting at 0, like 2x squared does, it starts up 3 on the y-axis because it was plus 3. Okay, and they worked all this out for you, and you can see it, but I want us to try to talk about how these would be related. Let's go ahead and graph y equals x squared, which is the parent function, and if you're not sure how to do that, you make a quick mini table. Let's just pick -1, 0, 1. We might have to pick 2. So -1 is x. Let's just say that's in the x's spot. So that's supposed to be an x. -1 squared. -1 times -1 is +1. So let's go put a dot at -1, 1. -1, 1. Okay. Plug in a 0. 0 squared is 0. So 0 is going to be at 0, 0. All right, +1. +1 times +1 is +1. So 1, 1 is going to be our next ordered pair. All right, I can see the start of the parent function of the parabola. Let's do one more. 2. 2 squared, 2 times 2 is 4. So you're going to put a dot at 2, 4. So over 2, up 1, 2, 3, 4. Okay, and we can go ahead and reflect this one over because now that I see where our parabola is going, you can see that this is the axis of symmetry, so it reflects here, it reflects here. This one is going to reflect over to this one. All right, so here is our graph of y equals x squared. I'm going to label it so you know which one this is. This is our parent function. It's the most basic parabola that we compare everything to. And now it wants us to graph the same one. This is y equals x squared, and so is this, except -3. So we are going to take each of these points and we're going to shift them down 3. That's down 3. That's down 3. That's down 3. Now, if I didn't know this, if I was like, I'm not sure how the other parabola is going to look, I want to show you how you would work it out. You would just make another mini graph, and you would say, I'm going to plug in, let's say, -1, 0, 1, and 2 again. -1 squared, -1 times -1 is +1, but then you have to -3 from it. 1 minus 3 is -2. So you'd put a dot at -1, -2, and that's what we did. Okay, you could keep going. 0 squared is 0, -3 is -3, and so we graphed that one on here as well. So you always start it by making a table, but if you can look at these equations and know much quicker, hey, I know exactly what this one's going to do. It's going to be the same, but it's going to shift down 3 because it's -3. It's not getting any wider or narrower because we're not multiplying that first number by anything. Instead, we are adding a number at the end of it, which is what moves it up and down the graph. Okay, The lesson review is doing a bunch of these. I don't think we need to do all 4 because I want you guys to try to practice some on your own. So I'm going to just pick a couple. I want to do 1 and 3. So you can try 2 and 4 on your own if you want to, but that's just more practice that we're going to do more of anyway. For this video, I'm going to do number 1 first, and then we'll do number 3, and we'll look at the graphs. So number 1, I'm going to make a table. Oh, it also says identify the vertex. So here's my table. I'm going to choose, why not? -2, -1, 0, 1, and 2. Those are just good choices to pick for your x values. I'm going to plug it in, but do order of operations. So you have to square it first and then come back and times by my -3. So x squared, if x is -2, -2 squared is -2 times -2, which is +4, times -3 would be -12. Yuck. That one's going to be way off my graph probably. -2, -12, -2, yeah, that's going to be way down here. So that one won't even fit on the graph. Let's try -1. -1 squared is -1 times -1, which is +1, times -3 is -3. That one will fit on my graph. -1, -3 is to the left 1 and down 3. Okay, let's do 0. 0 times itself is 0, times -3 is also 0, so 0, 0 is probably my vertex. All right, 1 squared is 1 times -3. Yep, that was my vertex. These are just going to open back up. You can see that it's going to be, our next one would be -12 because it goes, once it hits its vertex, it opens back up. So we're going to graph the dot here, and then our next one would also be way down here. So this is a very narrow graph. It is stretched, and we should have known that because it is stretched 3 times bigger than the parent function because there's a 3 being multiplied at the front. The other thing you should have known is that it was going to open going down because it is a negative. So before you even graph these, it's a great idea to get in your head a picture of what you think it might look like. Okay, let's identify the vertex. It's right here. It's a maximum. It's a maximum vertex, and the vertex is at 0, 0. All right, let's do this last one. In your head right now, think about whether you think it's going to be stretched out skinnier or kind of squashed a little flatter. And then think, if it's going to add 2, is it going to be shifted up 2 or down 2? So think about in your head what this is going to look like, and let's go ahead and make a table, and let's just see. So let's say we're going to pick -2, -1, 0, 1, and 2 for our x values. Let's plug one in at a time. -2 for x. So -2 squared is -2 times -2, which is +4. Half times 4, or half of 4, is 2. 2 plus 2 is 4. So our first dot is going to go at -2, +4. So I'm going to go to the left 2. Actually, I'll do it on this graph in case you want to do the other ones. -2, +4. All right, let's go ahead and try -1 now. -1 squared is -1 times -1, which is +1. Times half, which is just half, plus 2, which is 2.5. Yuck. That's not going to be any fun to graph, but let's do it anyway. -1 up 2.5. So -1 up 1, 2.5. Okay, 0 is going to be a little easier. 0 times this is 0, times this is 0, but then you have to add 2. So 0 plus 2 is 2. So we need to put a dot at 0, 2. So go 0 up 2. Ooh, this is squashed. I hope you guys see that that's going to be a little rounder, a little flatter, because it's half. Okay, and then let's try 1. 1 squared is 1, times half is half, plus 2 is 2.5, so here's where it's going to open itself back up. So then we know that the 2 would be 4. So 1, 2.5. If you don't believe me, go ahead and work it out. And then 2 up 4. Okay, so it's not only a little flatter and wider because it was half, but it has shifted up 2 from the origin because it was plus 2.